Hello everyone, my name is Dian Chen. Here I'm going to introduce our work, Contrastive Test Time Adaptation at UC Berkeley. My collaborators are Dequan Wang, Trevor Darrow, and Saina Ibrahimi. First of all, why is test time adaptation interesting? Because domain shifts happen in natural data, causing degradation in the performance of our model trained on the source domain. So, when facing various kinds of distribution shifts, we want to reduce such effects and remain performant on the target domain. More importantly, test time adaptation does not require access to the source data, which makes it extremely useful when source data is no longer available. For example, we might not always have access to source data because of data privacy, limited transmission bandwidth, etc. In such cases, the workflow of TTA is simply to take any model already trained on source and adapt it with only unlabeled target data. The simple and modular workflow of TTA makes it very practically appealing. However, what makes test time adaptation appealing also makes it challenging, because now the source model is our only proxy to the source domain. So, how should we reuse the knowledge learned from the source? And, apart from getting strong performance, what properties are also important in TTA algorithms? To answer these questions, we introduce our solution, Adaptation, which performs joint self-supervised contrastive learning at test time and online pseudo-labeling with refinement. The intuitions are that instance discrimination helps learn a target representation and hence decision boundaries, and useful priors in the pseudo-labels facilitates knowledge reuse. Here is the framework of our proposed AdaContrast. At test time, it takes in target images and optimizes a total loss of 3 terms. For the joint contrastive learning, we initialize the target model with the source model weights and perform instance discrimination with a momentum model and memory queue. Meanwhile, same class negatives indicated by the pseudo-labels are excluded. This helps the model to learn better representation on the target data. As for the pseudo-labels, we produce them online at each iteration. The pseudo-labels are refined by aggregating knowledge of their neighbors in a target feature space, namely averaging their probabilities before taking the argmax. This helps the model to bootstrap with the latest progress and significantly more accurate pseudo-labels. We also apply additional regularizations to facilitate learning, namely, weak-strong consistency is enforced in the self-training term, and the third term encourages diversity in the model predictions. As a result, our proposed AdaContrast achieves state-of-the-art performance on 2 major domain adaptation benchmarks, VistaC and DomainNet. We surpass the previous methods by a large margin. Apart from the state-of-the-art performance, AdaContrast also has a series of desirable properties for test time adaptation. First, compared to entropy-based methods, it produces a much better calibrated model on target. Second, it is memory efficient, requiring as low as 4% of the target dataset size to achieve state-of-the-art performance. Third, it's robust to hyperparameters, achieving similar performance with a wide range of choices. Last but not least, it adapts very quickly compared to the generative methods and has strong performance in online TTA settings when data arrives in a stream. All the properties above make AdaContrast not only a state-of-the-art but also a practically appealing algorithm. Thank you for listening.